What do squids, the Guinness World Records, magnets, and the brain have in common? We will find out in this video covering magnetoencephalograms. My lovely student Lily will be joining us. Let's start! General description. Your brain has around 90 billion neurons, and every time you speak, think, hear, or encounter any stimulus, your neurons start firing, interact with each other, and sending messages to help you react. Neurons make messages using electricity, creating small temporary currents and by extension, very weak magnetic fields. These magnetic fields can then be measured and visualized using magnetoencephalograms, typically referred to as MEGs. MEGs are used in research, surgery, and for diagnosis. They are often paired with other anatomical mappings of the brain obtained from devices such as magnetic resonance imaging or MRIs to gather information about the brain's activity and structure. MEGs are a multifaceted tool that I cannot wait to get into. Let's start with history. Many figures contributed to the development of MEGs. Due to time constraints, this video keeps it short. However, further research is encouraged on the list beside Lily. MEGs grew from decades of research. However, Dr. David Cohn was the first to measure the human brain's magnetic fields with a magnetometer in 1968. A magnetometer is a device that detects both the strength and direction of a magnetic field. Fun fact time! Dr. David Cohn won the Guinness World Record for measuring the weakest magnetic field twice. He collaborated with James Zimmerman to measure these weak magnetic fields of the brain using both magnetically shielded rooms and helium-cooled superconducting quantum interference devices, called squids, creating the first MEG circa 1970. As the decades passed, MEGs became commonplace in both neuroscience centers and research hospitals due to their ability to map the brain with millimeter-level precision in millisecond intervals. MEGs help with researching neurological conditions such as epilepsy, as well as analyzing behavioral patterns and cognitive functions. Physics concepts. MEGs have many physical, biological, and chemical applications, and this section will explain how they relate to MEGs, starting with biology. Lily, quick, define current. Current is the rate of electric charge passing through a conductor measured in amperes. Good. And if you have taken a grade 12 biology course, you know that similar to a wire, your neurons can carry charges too. Neurons move charged potassium and sodium ions, forming an electrochemical gradient during an action potential, which we know as the firing of our neurons. These moving, charged ions create a temporary electric current and magnetic fields. And since the current produced is temporary, it creates a changing magnetic flux. To relate this to MEGs, we must talk about the law of induction. The law of induction, commonly known as Faraday's law, states that a changing magnetic flux can induce an electric current in a conductor. Magnetic sensors like squids, OPMs, do not measure our brain's magnetic fields directly. They instead detect changes in magnetic flux that induce currents within their coils, and then convert them into brain activity signals. Also, superconducting helium cools squids, sensitizing them to detect these flux changes. Ah, yes, question? What is different about magnetic fields and electric fields, especially when it comes to MEGs? To answer that, let us do a comparison of electric and magnetic fields. To compare the two, first recall conductivity and resistivity. Conductivity means that some materials such as silver, copper, and gold are conductive. That means charged particles flow easily through them. Conversely, resistivity is the resistance of electron flow and occurs in insulating materials. Although our neurons are excellent conductors, our skull and other tissues act as insulators. They weaken electric fields with distance. Electroencephalograms or EEGs use scalp electrodes to measure electric fields of the brain. However, the brain's insulating tissues weaken and distort electric fields before they reach EEG electrodes, resulting in blurry and imprecise activity readings. Additionally, recall that electric fields represented by epsilon are inversely proportional to distance r squared, meaning that as distance increases, the magnitude of the electric field decreases rapidly. Magnetic fields also decrease in strength with distance, but do not rely on tissue conductivity and can pass through brain structures to the magnetic sensor without much distortion. This is why MEGs have millimeter-level precision. Magnetic field strength. Lily, quick, give me the magnitude of Earth's magnetic field. 25 to 65 microteslas. Correct. What if I told you the brain's magnetic field strength was 1 billion times weaker, measured in femtoteslas? MEGs need to pick up these weak magnetic fields. Similar to how compasses always align along the stronger external magnetic field, magnetic sensors will only interpret the strongest reading they receive. For brain imaging, blocking out Earth's strong magnetic field is essential, but how do they do that? You previously learned that radiation can be blocked with atomically dense materials such as lead. Guess what? Magnetic fields too can be effectively absorbed and redirected using magnetically permeable materials such as mu metal. With this metal, we can detect the brain's small magnetic fields. This is why MEGs occur in shielded rooms. Shielded rooms? Sounds expensive. Is it really worth it? Interesting angle. Let's look at the pros and cons, starting with the pros of cost. Liquid helium requires significant energy to produce and store, making traditional squid-based MEGs expensive to operate. Luckily, newer OPM MEGs avoid cryogenic cooling entirely. OPM systems greatly reduce costs, are easier to maintain, and could make MEGs far more accessible in the future by lowering both installation and operation costs. Cons of cost. Unfortunately, OPMs are a recent promising technology, and most current MEGs are costly costly, non-portable squid systems that require shielded rooms and liquid helium cooling, costing around 200,000 USD annually and around 3 million to install. Consequently, roughly 200 MEGs exist worldwide, often forcing long-distance travel and limiting access to MEGs for medically fragile or non-mobile patients. Pros of environmental impact. MEGs and OPMs in particular are non-invasive since they require minimal to no incisions, injections, contrast agents, or radioactive material. Thus, MEGs are generally safe and pose no threat to the environment when used because their procedures involve no radioactive or chemically volatile materials ending up in landfills. Cons of environmental impact. The manufacturing of MEG can damage the environment. The magnetic shielding, often consisting of mu metal, mainly nickel, molybdenum, and copper alloy, involves the extraction and refining of common metals. These processes can disturb ecosystems, causing soil erosion, air pollution, water contamination, and habitat destruction due to mining and refining practices that create harmful dust and chemical waste. Pros of societal impact. MEGs boast millimeter precision mapping with millisecond-long intervals. Since the brain sends signals in rapid succession, MEGs pinpoint the exact time and location of abnormal cognitive activity, facilitating accurate diagnosis of neurological disorders and research concerning links between brain structure and behavior. Additionally, such precision allows surgeons to pinpoint exactly what to cut and what to avoid when performing surgeries near critical areas of the brain. Cons of societal impact. Deep structures like the hippocampus and brainstem are hard to interpret because surface magnetic activity creates noise that interferes with results. This makes MEGs less accurate for locating deep abnormalities, reducing their diagnostic value, and often requiring additional imaging tests, which increases patient stress and delays diagnosis. Current and future research. Current research. OPMs, or optically pumped magnetometers, were invented by researchers worldwide and in 2017 were successfully miniaturized. These are cheaper, wearable, more accessible, and lightweight MEGs. Currently, various universities, such as the University of Nottingham, are researching how to make more portable, wearable MEGs that could enable bedridden patients to obtain brain imaging with ease. It would also accelerate research on neurological conditions such as dementia, boasting many applications in clinical and research settings. Future research. Due to neurological disorders and conditions such as ALS, spinal cord injuries, strokes, traumatic brain injuries, and locked-in syndrome, patients lose their ability to communicate or move. Institutions such as Ulster University have begun to invest in researching how to integrate MEG's millisecond-level precision brain readings with prosthetics, robotic arms, and other communication devices in hopes of one day offering a way for these patients to partially regain the ability to move and communicate. Concluding remarks. Pioneered by James Zimmerman and David Cohen, MEGs have unlocked the ability to observe magnetic activity in the brain with high speed and accuracy. Generally, MEGs have furthered research and diagnosis of neurological conditions, optimized surgical procedures, and continue to provide insight into how the brain's anatomy relates to behavior, while causing no direct pollution when in use. MEGs' benefits are hindered by their high cost, low availability, poor depth analysis, and pollutive manufacturing. Current research shows promise of making MEGs more widely available, portable, and versatile thanks to new wearable sensors and OPMs. Lastly, future research for the integration of brain readings into prosthetics could offer revolutionary benefits to those who cannot move or speak. Hopefully, this video taught you a few things about MEGs. Thank you so much for watching! This was made with CapCut and BandLab.